Jupiter. Jupiter possesses the strongest gravity of any planet in the solar system, with a surface gravity of approximately 24.8 meters per second squared, or about 2.5 times Earth's gravity. This extreme gravity is primarily the result of Jupiter's enormous mass, which exceeds 318 times the mass of Earth and is greater than the combined mass of all other planets. Although Jupiter's radius is very large, its immense mass dominates the gravity equation, producing a powerful gravitational field even at the upper cloud layers. Jupiter does not have a solid surface. Gravity is measured at the level where atmospheric pressure equals Earth's sea level pressure. As one descends deeper into the atmosphere, gravity increases due to rising density and compression. However, beyond a certain point, adding more mass would cause the planet to expand rather than significantly increase surface gravity. For this reason, Jupiter is near the upper theoretical limit for planetary surface gravity. Jupiter's gravity strongly shapes the solar system. It influences asteroid belts, redirects comets, and captures objects into stable orbits. Its gravitational reach extends far beyond its immediate vicinity, making it a dominant dynamical force. Jupiter demonstrates how extreme planetary gravity arises from mass dominance rather than density alone. Saturn has a surface gravity of about 10.4 meters per second squared, slightly higher than Earth's, despite being the second most massive planet in the solar system. This relatively moderate gravity is surprising given Saturn's size, but it is explained by the planet's exceptionally low density. Saturn is composed mostly of hydrogen and helium, and its large radius spreads its mass over a vast volume, reducing gravitational acceleration at the cloud tops. Like Jupiter, Saturn lacks a solid surface. Gravity measurements are taken at the altitude where atmospheric pressure matches Earth's sea level pressure. Below this level, gravity increases as atmospheric density rises. Saturn's gravity is strong enough to hold an extensive ring system and more than 80 moons, but it is far less dominant than Jupiter's gravitational influence. Saturn illustrates a critical principle of planetary gravity. Size alone does not determine gravitational strength. Despite its immense volume, Saturn's low mass concentration limits its surface gravity. This makes Saturn an important counterexample when comparing planetary mass, density, and gravitational effects across the solar system. Neptune. Neptune has a surface gravity of approximately 11.2 meters per second squared, or about 1.14 times Earth's gravity. This makes it stronger than Saturn's gravity, even though Neptune is significantly smaller. The key reason is Neptune's high density and compact internal structure. Unlike gas giants, Neptune contains a large proportion of heavy elements such as water, ammonia, and methane beneath its atmosphere. Neptune has no solid surface. Gravity is measured at the upper atmosphere. Its relatively small radius combined with substantial mass produces a stronger gravitational pull than might be expected for its size. This gravity plays an important role in sustaining Neptune's dynamic atmosphere, which exhibits some of the fastest winds observed on any planet. Neptune's gravity also helps maintain its system of moons and faint rings. It demonstrates that planets with smaller radii but higher density can produce gravitational forces comparable to or greater than much larger planets. Neptune is a clear example of how mass distribution and composition are as important as total mass in determining planetary gravity. Earth. Earth's surface gravity, defined as 9.81 meters per second squared, serves as the standard reference for gravity throughout planetary science. Earth's gravity results from a balanced relationship between its mass and radius, producing a density sufficient to maintain a stable atmosphere and liquid water without creating extreme surface conditions. This gravitational strength allows Earth to retain essential gases, regulate ocean behavior, and support long-term geological activity such as plate tectonics. Earth's gravity also enables a stable climate by preventing rapid atmospheric escape while avoiding excessive atmospheric compression. Compared to other planets, Earth's gravity is moderate, but it falls within a narrow range that is highly favorable for complex life. Small deviations from Earth's gravity would have significant consequences. Higher gravity would increase atmospheric pressure and strain biological systems, while lower gravity would lead to atmospheric loss and reduced surface stability. Earth's gravity represents a rare equilibrium that supports habitability over geological timescales making it a benchmark rather than an extreme case. Venus. Venus has a surface gravity of about 8.87 meters per second squared, approximately 90% of Earth's gravity. This similarity arises from Venus's comparable size and mass. From a gravitational standpoint, Venus closely resembles Earth and demonstrates that Earth-like gravity is not uncommon among terrestrial planets. Venus's gravity is strong enough to retain an extremely dense atmosphere with surface pressures about 90 times greater than Earth's. While gravity contributes to this retention, the planet's atmospheric composition and runaway greenhouse effect are the primary drivers of its extreme surface conditions. Gravity alone does not explain Venus's uninhabitable environment. Venus highlights the relationship between gravity and atmospheric behavior. Earth-like gravity can support either temperate or hostile conditions depending on atmospheric chemistry and solar interactions. As such, Venus serves as a critical reminder that gravity is only one factor in planetary habitability, even when it closely matches Earth's. Mars. Mars has a surface gravity of approximately 3.7 meters per second squared, or about 38% of Earth's gravity. This low gravity is the result of Mars's smaller mass and radius. Over billions of years, Mars's weak gravity was unable to retain a thick atmosphere, contributing to the loss of surface water and long-term climate change. Lower gravity reduces escape velocity, allowing atmospheric gases to gradually leak into space. As a result, Mars today has a thin atmosphere and cold surface conditions. Objects on Mars weigh significantly less and physical movement requires less force, but the long-term effects of low gravity pose serious challenges for biological systems. Mars's gravity is not extreme in strength, but it is extreme in consequence. It has played a central role in shaping the planet's geological evolution, atmospheric loss, and present-day environment. Low gravity remains one of the primary obstacles for sustained human habitation on Mars. Mercury has a surface gravity of about 3.7 meters per second squared, similar to Mars, despite being much denser. This is because Mercury is significantly smaller, limiting its total mass. Its unusually large iron core accounts for much of its density, but density alone cannot compensate for small planetary size. Mercury's gravity is too weak to retain a substantial atmosphere, resulting in only a thin exosphere. This lack of atmospheric insulation leads to extreme temperature variations between day and night. The planet's low gravity also limits geological activity and surface renewal processes. Mercury demonstrates that high density does not guarantee strong surface gravity. A planet must have sufficient mass as well as density to generate significant gravitational pull. Mercury's gravity has strongly influenced its surface environment and long-term stability, making it an important example in planetary gravity studies.